Morning, we'll be doing chapter number 8, bonding and molecular structure. This is one of the most important chapters. Just like the others, plays a very important role in assigning formula and structure and describing the properties of compounds that are formed. And I'm going to share my screen with you so that we can start the exercise. Just before we start, I just want to tell you that as the time comes, we will be combining certain aspects of the structure to make it a bit more simplified and make it repetitive so that students become familiar with what are the types of questions to ask and then use the answers to predict the structure and the nature of the compound that is there. So the first question that comes is, what is a chemical bond? A chemical bond is a force that holds two atoms together. Now, the bonding occurs using the valence electrons. Valence electrons are the outermost electrons available to a particular atom in a given group. Electrons in an atom generally can be categorized as either valence or core electrons. Core electrons are the inner electrons that provide the shading from the nucleus and do not take part in any chemical reactions. It's the outermost electrons that are available that are involved in bonding. Atoms try to either get 2 electrons, a duplet, or 8 electrons in the valence shell, an octet. The Lewis symbol helps to track the valence electron and predict the type of bonds that can be formed. The valence electrons are available from the highest shell of the highest n value. The octet rule gives us a noble gas structure, NS2NP6, where N is the energy level of that particular group. Usually this is done for only A group elements, and A group elements are considered as the representative elements. And this is a simple system to keep track of electrons around atoms, ion, and molecules. This was invented by G.N. Lewis. And if you know the number of valence electrons in the valence shell of an atom, it is very easy to write the Lewis symbol for these atoms that are there. For example, if you have an atom, then first we put in the basic rules, draw the atomic symbol. This represents the atomic nucleus along with the core elements. Treat each box side as a box that can hold up to 2 electrons. Count the electrons in the valence shell. Start filling boxes. Don't make pairs unless you need to. So generally, we follow the Pauli exclusion principle and the Hans rule and make sure that every box has 1 electron before pairing occurs. Now, the position of where you place the electron is immaterial because all of those on a Lewis dot symbol represents the same electron. And it is called as a Lewis dot structure. You can place a dot, but if you want to differentiate electrons from other atoms, you can place another symbol, but at the end, they just represent the valence electrons. For the main group elements, the number of valence electrons is equal to the group number. Therefore, group 1A to 8A valence can be easily predicted from the periodic table. Core electrons are not involved in bonding. And as you can see over here, NS2, NS1 is group 1. You have 1 electron, and NS2 has 2 electrons, and the example is in group 2. The second row elements and the third row element are shown here. And the second group, beryllium, then you have boron, carbon, nitrogen, oxygen, fluorine, neon. And when it comes to neon, you have all Ns2, Np6 is filled. Just by looking at the general formula Ns2, Np, we can tell in which group an element belongs. Now, in group 3 also, it follows the same pattern. Below lithium on the periodic table, you have sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. And so you have the 2 groups, the shells are shown. When we consider chemical bonding, there are certain questions that need to be answered. First thing is, what holds the atoms in a molecule or an ionic compound together? Why are atoms and molecules often distributed in strange angles? Why are molecules 3-dimensional? Can we predict the structure of a compound? How does structure relate to chemical and physical properties? And these are generally the questions that one will be answering as we go along. Bonding, the forces that hold adjacent atoms together are of 3 types. The 4th type we are not going to discuss here, but these are the main types. First is the covalent bond, which is the electron sharing from the outermost shell. Ionic represents electron transfer from the outermost shell. Metallic represents the mobile valence electrons, because in this case, electrons are not associated with any atom. They just form a sea of cloud all over the atom, top, bottom, and the sides, so that the electrons are uniformly distributed. In most chemical compounds, electrons are shared unequally between the atoms. The boundary between covalent bond and ionic is somewhat subjective, but still we can differentiate it. Now, before we go further, let's look at the ionic bond. In ionic bond, an element loses the cation, an element which is on the left of the formula of the compound, loses its electron. So it loses an electron, and the anion gains the electron, forming the cation Na plus and Cl minus. Loss of electron is considered as oxidation, and gain of electrons is considered as reduction. And so we can describe the oxidizing and reducing agents. Furthermore, since every element tries to complete its octet or has a noble electronic configuration, that means Ns2 Np6 is filled, you will find that a cation has an inert gas structure that is before it, while an anion will have the inert gas or noble gas structure following it. So this is a quick study for a checkup how many electrons are there in phosphorus, chlorine, and carbon. And you can just go to the periodic table, remember the group. The electronic configuration for carbon is element number 6. Has the electronic configuration 1s2, 2s2, 2p2, and therefore under the total valence shell electron is 4, and therefore carbon belongs to group 4. And so here again, make sure you know the rules for self-check. And so make sure that you can understand and differentiate a possible correct Lewis structure by ensuring that each element either completes its tuplet. In the case of hydrogen, can take only 2 electrons and no more, and all other elements will try to take surround itself with 4 electrons. And these are different types of structures and for practice. Now, before we go any further, we have to determine what is the nature of the bonding that is there. Why? Because we say that compounds are formed by either loss and gain of electrons or sharing of electrons. If it is shared, then generally the sharing of electrons is unequal unless and until both the atoms are of the same type or belong to the same group. And not only the same group, but it's in a same element itself. So then there is no change in the bond strength, but otherwise, because the difference in polarity, you will see. Now, the electronegativity measures the relative tendency for an atom to polarize a bond. It follows Z effective on the periodic table. And what is Z effective? Z effective is the actual force of attraction experienced by the outermost electron due to the presence of the core electrons that are in a given atom. And so generally, for a very simplified formula, Z effective is equal to atomic number Z. Take away the number of core elements and you get an approximate idea of the Z effective value. The ability of an atom in a molecule to attract electron to itself. We have ionization energy is a measure how hard an atom holds on to its electron. Electron affinity, how strong an atom attracts an electron to itself. And so electronegativity assigns a numerical value to the force of attraction for an atom to bring the electron towards itself. Generally, the strength of the bond or the nature of the bond is indicated by delta electronegativity. So usually the anions are the ions, or the atoms, non-metallic atoms are the elements that attract electron towards themselves and form the anion. And therefore, we have the ionic compounds lose or gain electrons, and therefore the charge is a measure from 0 to 3.3, with 0 to 0.5 as nonpolar, between 0.5 and 1.7 as polar covalent, and above 1.7 and between 3.3, it is ionic. So nonpolar are generally formed with bonds between two identical atoms that are there. So they do not pull or acquire a dipole moment or a positive and negative end. A polar molecule will acquire a positive and negative charge because the anion has a greater attraction for the electron as compared to the cation. Now, electrons may not be shared equally. This is based on the electronegativity difference between the two elements forming the bond. If the difference is 0, then it is covalent. If the difference is greater than 1.7, it is ionic. And between 0 and 1.7, as stated before, they are polar covalent. Electronegativity tells us how much a particular atom wants electron. Electronegativity increases from left to right across a period and decreases down the periodic table in a group. A molecule with no polar bonds is a nonpolar molecule. A molecule with one polar bond is a polar molecule. If the individual bond dipoles do not cancel, then the molecule is polar. If the individual bond dipoles cancel, then the bond is nonpolar. If there are lone pair electrons on the central atom, the molecule is polar. All these definitions of bond, dipole, lone pair, polar, non-polar, once we start drawing the structure, it will become much more clearer. The concept of polar and non-polar arises because of the fact that like dissolves like. For example, oil and water are non-polar solvents because water is polar, oil is non-polar, and therefore they do not mix. On the other hand, if the molecules are polar, like water and alcohol or ethanol, they mix because both of them are polar, and so they will mix with one another. When we talk about polarity and electronegativity, it is basically a distortion of the electron cloud that exists between the two atoms forming the bond. If there is no distortion between the two atoms, then the electron cloud is uniformly distributed, and therefore you have delta electronegativity as equal to 0. For a polar covalent bond, the ion that is more polar will pull the electron towards itself, and we find that the delta X lies difference is of a higher value, and higher the value, the more greater the ionic nature. And so always we subtract the higher of the anion electronegativity, take away the cation electronegativity, and this will give us a chance to describe the nature of the polarity of the bond that is there. A difference in electronegativity of 0 indicates that the bond is purely covalent. There is equal sharing of electrons. A difference between 0.1 to 0.3 indicates the bond is non-polar covalent. Difference between 0.4 and 1.7 indicates that the bond is polar covalent. And the difference greater than 1.8 indicates the bond is ionic. These numbers you may want to remember, at least the range, so that you can identify. The polarity of the individual bonds in a molecule determines the overall polarity of the molecule. All homonuclear diatomic molecules are nonpolar. What do we mean by homonuclear? That means their atoms are the same. For example, H2N2I2. So if you subtract, if there are two I atoms, and if you subtract the electronegativity value, then you will get 0. And therefore, these atoms have symmetry when divided, the top and bottom, as well as the right and left are mirror images of one another. One also knows the molecule is nonpolar because the bond is nonpolar. So these are some of the criteria that you have to look for when you are trying to describe whether the molecule is polar or nonpolar. Now, fluorine has the largest electronegativity value, and it is 4. It is assigned an electronegative value of 4, and you can look at the chart for the electronegative values for group 3A, 4A, 5A, 6A, and 7A. And you can see which has a higher value, and each are definitely every other value is less than that of fluorine. Electrons, this means that the electrons, if you take HF, for a compound like HF, the electronegativity will be, difference in electronegativity will be 4.0, take away 2.2, which is 1.8, and therefore we know that the electron distribution is towards the fluorine atom, and therefore this more polarizes the molecule. Fluorine has a more tendency to attract electrons, is the negative end, and hydrogen is the positive end. And so just in this way, we can compare the polarity of different bonds just by finding out the delta En chi by using the electronegativity table, and then say which bond is highly polar, increasing order of polarity or decreasing order of polarity. So you can see that HF is 1.8, carbon fluorine is 1.5, and oxygen fluorine is 0.5. So in terms of a polarity, HF is the largest polarity, followed by CF and then HF, OF. And here is another Van Arkel-Ketelaar diagram, which shows the polarity and this, and also the nature of the element. On the left of the triangle has three vertices. On the top, you have the ionic. To the right, you have the covalent. And to the left, we have the metallic. And you can see the difference in electronegativity. And so if you follow the chart, you can find out where each block gives you the average electronegativity and nature of the element that is there. And with that, the remaining items are for you to just self-check yourself and make sure that you understand how to calculate the delta chi values for electronegativity, and all the other items are based on this so that you can understand. And with that, I'm going to stop and then show you in the next unit how to draw the Lewis dot structure.